Hi everyone, so welcome to the second installment in our DC machine section. By the end of this session, you should be able to draw the equivalent circuits for the main DC machine configurations and develop the circuit equations pertaining to those configurations. So the three configurations, very simple: series, shunt, and separately excited. And by configuration, what we're talking about is the configuration of the field and the armature. So for a series configuration, the field is placed in series with the armature so that the same current goes through both of them. And the voltage, the terminal voltage, is across both of them together. For the shunt configuration, the field is placed in parallel with the terminal, with the armature, so both of them have the same voltage. And for the separately excited, you simply have them separately and they are powered from different sources. That is why we say they are excited separately. There is also a compound configuration where you have a combination of series and shunt. So in that case, you have the series winding here. You will also have some shunt winding like this, which is across, it will be here across the configuration as well. So across the winding as well. So let's look at separately excited windings to start with. Here we have the field windings composed of a large number of turns with small cross section, and the field and armature circuits are excited by different sources. So it doesn't matter how you vary the voltage here or the current here, you get the same current in the field. And this does not happen, of course, if you have a series or shunt configuration. Now, the shunt machines, we have the field and armature circuits connected in parallel to each other. This is similar to separately excited if you think about it. It functions just as if you had a separately excited machine, but you apply the same voltage to both the field and the armature. It would be exactly the same as a separately excited, as a shunt machine, sorry. And for the series machine, now sorry, let me just go back. One of the important things here is that the field must be able to take the full rated voltage of the machine. So it's important when you design a shunt machine to make sure the insulation and so on could withstand the voltage levels that you're going to apply to the machine. Now for the series machine, we have the opposite. We have a small number of field windings with very large cross section, and this is because we don't want to drop a lot of voltage over the field, but we do want to carry a large amount of current, because the same current which is going into the machine is the same current which goes through the field. So as the loading of the machine increases, that is, as IA increases, which means more power is going to the machine, it means the field current increases, so the field becomes stronger, which is good in terms of your torque. So these are the basic configurations for compound machines. As we said, you have both shunt and series windings. Now the field, we looked at previously the armature circuit. The field circuit is very similar. We have the voltage across the field winding is IR plus L di dt. Now again, since this is a DC circuit, if you think about a separately excited machine, after you power on the circuit, once those transients die down, then you have no di dt, and you just have I field by R field. So if you want thinking about where did that L di dt go, it's because it's a DC circuit, so di dt is 0. So that is basically all you have for the model of the field circuit. So you could see DC machines very simple. We just have one or two resistors in the model for the equivalent circuit. Now we're going to look at some derivations for the speed and the torque of the machine. And to do this, we have to go back to our power equation. We know that EAIA is equal to T E omega m. Again, this is the electromagnetic torque, and it does not we have not subtracted yet the friction and windage and so on. So this is the electromagnetic torque, and we have the voltage and current across the armature, EA here. And I know EA from my circuit diagram is equal to VT. This I will have an RA here. EA is equal to VT minus IARA, and that is equal to Ka phi omega m. If you don't remember where this came from, you could go back to the last video and look at it. You'll see how we derived it from the armature reaction equations. So I have EA is equal to VT minus IARA. I also, which is Ka phi omega m, and I also know TE is equal to Ka phi IA. Remember, these are the two defining equations we looked at the end of the last video. So I could substitute now for EA and for TE in this equation. This comes straight out of here. I just make omega m the subject of the formula, and I substitute for EA in here, and I substitute for TE here, and I end up with VT minus IARA on Ka phi. So I could just separate these two, and you'll see I have VT on Ka phi minus IARA on Ka phi. So this is the equation we use for the speed of the machine. And if I want to look at the equation for the torque of the machine, I know TE again is equal to Ka phi Ia. I know Ia is VT minus EA on RA. That is just the voltage across the armature resistor divided by the resistance. So V is equal to IR is basically what we are looking at here. And I substitute this, and I get Ka phi VT minus EA on RA. And of course EA I know is K phi omega m. So I could substitute that in, and that gives me this equation for the torque. So these you could derive them easily if you just know a few equations. One equation here, then you need to know the circuit equation and the equations relating the armature voltage and the velocity and the torque and the current, that is relating these parameters through the motor constant. So, and once again, this Ka phi that you're seeing all over here is sometimes given as a single value, Ke or Kt. Now, based on these equations, we could look at some different operating points of the machine. So we could look at no load. So if there's no load, it means Ia is 0. And I have omega m here. If Ia goes to 0, this whole thing goes to 0. And then I have omega m is equal to Vt on K phi. And if I have a torque change of Tm, then I have the change in omega naught is equal to IARA on K phi. That is if the torque changes, which it just means if you have a change in the current. So remember, you could relate Ia to the torque because T is equal to Ka phi Ia. So if you have a substitute for Ia, you will get Ia is T on K phi, which gives us RATM on K phi squared. So for a change in torque, we'll just get this change in speed. This part remains constant. So that is two conditions for velocity, and you'll see here that the change in speed when torque changes is dependent on Ra. So if you have a very small Ra, if the armature resistance is very small, then you could have almost no change in speed when the torque changes, which is something very desirable. It means regardless of the torque fluctuating on the machine, it could run at the same speed. The next thing we want to look at is what happens to our torque for different conditions. So we have at omega equals 0, which is when the machine is starting. When the machine is starting, the speed is 0. We know that Ia is equal to Vt minus Ea on Ra. When the current is starting, Ea will be 0 because Ea is equal to Ka phi by omega m. So if omega is 0 when it's starting, then Ea is going to be 0 and Ia will simply be Vt on R. That is the starting current. And given that starting current, we could look at the torque, and the torque will be, or we could just substitute it directly into here, and we'll get the torque, if this goes to 0, as KAVT on RA. And again, if the armature resistance is very small, it means you could have a very large starting torque. So small armature resistance gives you both a very good speed torque characteristic, very low torque variations with very low speed variations with changes in torque, but it also gives you a very high starting torque. So that is for separately excited machines. For shunt machines, remember we said the shunt machines, they behave very similarly to the separately excited machines. The main difference is that for a separately excited machine, you could change independently the voltage on the field and the voltage on the armature. For the shunt machine, it is as though you tie those voltages together so that it is the same arrangement. It's just that you have the same voltage always across the field and across the armature. So the equations then are exactly the same as the separately excited machine. So the same things we just did, they also hold for the separately excited machine. You don't have to derive anything differently. And here, when you have a small RA, as I mentioned before, you're going to have a very small speed deviation with torque, with changes in torque. In fact, it's almost constant. So this is the same as I mentioned before as the separately excited machine. For the series machine, here, remember, for the field windings, we have a few turns with high current. The field current changes with the loading because the loading means different torque, which means different current, since T is equal to omega m multiplied by Ka phi. So if the, not omega m, I. So as the torque increases, it means the current also increases. And since it is in the field winding is in the series path of with the armature winding, it means the field current increases with the armature current. So this allows us to have very high speeds at no load, and you have a very high starting torque as well. So because your field winding has a very, very low impedance, and this is something just for your general interest. It can also be it can also work with AC supplies, because the field winding, the polarity of the field winding switches with the polarity of the armature current as well. So for these equations, essentially all you do is you replace Ra with Ra plus Rf. So remember, for the shunt winding, you had the armature. This was this was your circuit, RA, EA, and now you have and VT for the separately excited, and you had your field here with your EF. Now, if we take this field and we put it in series here, then the same analysis holds with VA, EA, and so on. It's just instead of RA, now the series resistance is RA plus RF. So that is all you need to do in the equations. You just go back through the equations and you swap RA with RA plus RF in all the places you see it, and you end up with the series characteristics. So you could go ahead and do that and write out the equations in your notes. Now, these different combinations, as we mentioned before, give you different sort of speed torque characteristics. And this speed torque characteristic is something you're going to come across for all the machines we do. Once you're looking at machines, you want to know how the speed is going to change with the torque, because different applications will demand different sort of characteristics. So for the separately excited machines as well as the shunt machines, you have a linear, almost constant, not constant, almost constant characteristic. So regardless of the torque, you get a uniform speed. For the series, you get a very high starting torque. As we talked about, you get a very high starting torque, but it drops quickly. So remember, as the torque increases for the series machine, it means the current increases and through the field, and as the current increases, the voltage is going to increase as well. So you're going to get a lower voltage drop, which means your EA is going to decrease, which is going to decrease your omega M. And compound machines, you could do combinations of the shunt and the series, so you end up somewhere in between. Now, that brings us to the end of this section, and by now you should be able to draw the equivalent circuits for the main DC machine configurations, and these are shunt, series, and separately excited, and you should be able to develop the circuit equations for the main DC machine configurations. Now remember, whenever we're dealing with DC machines, it's just a small set of equations that we look at. If it's operating as a motor, we have VT is equal to EA plus IA RA, or RA plus RF if it is a series machine. If we don't have the series configuration, then it's just RA, shunt or separately excited. We also know that EA, which is the armature voltage, this is the voltage induced by the rotation of the conductors in the magnetic field. If that EA is equal to K A phi omega M, and we have TE, which is equal to K A phi IA. So these are the basic equations we work with, and from these equations we could figure out everything in the DC machine. So this is what you'll need to know for all the questions that we have to answer. And basically, oh, and I forgot one more, which was EA IA is equal to TE omega M. Electromagnetic power is equal on the electrical side is equal to the electromagnetic power on the mechanical side. So these four equations are what you need to know. What are the things that would define the DC machine? And remember, the equivalent circuit is very simple. You have your armature and your terminal voltage. And that's basically it. So as long as you know this, you could derive your circuit equation. So next we'll be looking at some examples. And then you'll get to see how we use these equations when we have an actual question to work out, when we have some problem, we need to calculate the torque or what are the currents and so on, how we apply this theory to it.